Inside an electron ionization mass spectrometer, the environment is a high vacuum. A neutral organic analyte is injected into this chamber, completely isolated and ready for analysis. Struck by an electron beam fired at 70 electron volts, the extremely violent collision forces the molecule to eject an electron of its own, converting the neutral analyte into a positively charged parent radical cation. That 70 electron volt impact transfers a massive amount of internal energy. The resulting radical cation is left highly excited, vibrating intensely, and primed to shatter. This chart displays the resulting electron ionization spectrum for an aliphatic molecule known as octanol. On the far right side of the graph, we see a peak at a mass-to-charge ratio of 128. This represents the molecular ion, the intact octanol molecules that survived the bombardment without breaking apart. But the dominant feature of this data is located on the far left. The base peak, the most abundant fragment produced by the collision, sits at mass-to-charge 44. This peak presents a mathematical impossibility under basic assumptions of how molecules break. Octanol is a straight-chain aldehyde. If you simply snap single carbon-carbon bonds along that chain, you cannot produce a fragment weighing exactly 44 mass units. The existence of this peak proves a core concept in spectrometry. Despite the extreme violence of electron ionization, the destruction is not random. The molecule fragments according to strict thermodynamic and stereochemical laws. To understand where that anomalous peak comes from, we first have to map the baseline rules of direct bond cleavage, and then uncover the complex intramolecular mechanisms that dictate advanced fragmentation. Mastering these deterministic rules allows a chemist to reconstruct the original geometry of a molecule from the resulting collection of fragments. When a radical cation shatters, it follows a primary directive. It will break apart along the path of least energetic resistance to form the most stable possible resulting cation. The most straightforward path is homolytic cleavage. This homolytic cleavage occurs when a bond breaks evenly, with two shared electrons transferring independently to adjacent atoms. We see this clearly in the alpha-cleavage of a carbonyl group. Single electrons, indicated by fishhook arrows, shift to form a new double bond while breaking the carbon-carbon connection. This process ejects a neutral alkyl radical and leaves behind an acylium ion. Because the positive charge is stabilized by resonance with the oxygen atom, this is a highly favorable outcome. The alternative mechanism is heterolytic cleavage. Here, a bond breaks unevenly, and an entire electron pair is transferred entirely to one atom. Heterolytic cleavage dominates when an electronegative heteroatom, like a halogen, is present in the structure. The halogen forcefully pulls the entire electron pair toward itself, severing the bond and leaving a carbocation behind. Both of these mechanisms seek out structural stability. If an aromatic ring is present, cleaving the bond beta to that ring yields a benzyl cation at M-Z91. The positive charge becomes highly delocalized across the cyclic structure, making it exceptionally stable. When a molecule has multiple potential breakpoints, it typically adheres to the largest branch rule. It will expel the largest possible alkyl branch as a neutral radical, thereby maximizing the stability of the remaining charged fragment. In all of these simple cleavages, whether homolytic or heterolytic, the resulting charged product is an even electron cation. While these basic rules map out a significant portion of a typical mass spectrum, they reach a strict limit. They completely fail to account for the massive, even mass anomalous peaks generated by long-chain systems.
This returns us to the mystery of the octanol spectrum. We have a dominant, even mass peak at M/Z44 that basic single-bond snapping cannot produce. The mechanism responsible for this is the McLafferty Rearrangement. This diagram outlines the precise geometric prerequisites required to trigger the event. The molecule must possess a pi system, in this case a carbonyl group, and an available hydrogen atom located exactly on the gamma carbon, 3 bonds away. Because the aliphatic carbon chain is flexible, thermal energy causes it to bend toward the oxygen. This folding physically brings the gamma hydrogen into close proximity, forming a highly favored, sterically unhindered 6-membered transition state. Once the geometry aligns, the radical oxygen atom homolytically abstracts the gamma hydrogen, pulling it across the gap. That initial hydrogen transfer sets off an immediate cascade of electron shifts, rippling through the transition state. Lee's shifting electrons force a targeted cleavage at the beta carbon bond, severing the hydrocarbon tail. That tail is expelled as a neutral alkene, like 1-hexene. What is left behind is a highly stable enol radical cation. Because it retains an unpaired electron, it is an odd electron ion, which dictates an even mass number. It registers perfectly at M/Z44 for unbranched aldehydes and M/Z58 for methyl ketones. The mathematical anomaly is solved. The McLafferty peak is a definitive structural flag. Its presence proves the exact existence of a flexible 3-carbon aliphatic chain attached directly to a carbonyl group. If the McLafferty rearrangement requires a flexible chain to execute a hydrogen transfer, cyclic molecules are bound by a completely different set of structural rules. For cyclic olefins, such as cyclohexene, the dominant fragmentation pathway is the Retro Diels-Alder reaction. The key mechanical difference here is that this is a concerted process. The ring does not unzip bond by bond. Instead, dictated by precise electronic rules, 2 separate carbon-carbon bonds within the cyclic system cleave at the exact same time. Unlike the folding mechanism we just examined, there is absolutely no hydrogen transfer during a Retro Diels-Alder fragmentation. This synchronized cleavage completely splits the ring, ejecting a neutral dienophile. For cyclohexene, that ejected molecule is ethylene. The positive charge remains with the fragment that has the lower ionization potential. In these systems, that is typically the resonant stabilized conjugated diene. In a simple cyclohexene system, this resulting diene radical cation yields an intense, distinct signature peak at exactly M/Z54. By utilizing this concerted 2-bond cleavage, the Retro Diels-Alder reaction cleanly dissects cyclic topologies, revealing the architecture of rings that would otherwise resist normal fragmentation. A mass spectrometer is a highly precise structural scalpel. The data it captures is defined by 2 primary pathways a radical cation can take, an instantaneous shattering, or a delayed, stereochemically coordinated shift. Simple cleavages strip away branches driven strictly by electronegativity to find localized resonance stability. The McLafferty rearrangement relies on a highly specific 6-membered transition state, flagging the exact length and substitution of a carbonyl's aliphatic chain. And the Retro Diels-Alder mechanism cleanly dissects complex cyclic topologies through a synchronized multi-bond cleavage. Spotting the diagnostic even-mass odd electron ions produced by these coordinated rearrangements is the defining skill in advanced spectral analysis. By understanding the geometries and energy states that trigger these transitions, chemists resolve the chaotic wreckage of a spectrum into a single specific molecular structure.